let us start. Can also get it on Twitch, by the way. Quality might be better. Yeah, we last time we were scanning through a few applications of point locations, and I'll mention very briefly a few more, and then we'll spend quite some time meditating on Convex Hull and properties of Convex Hull and combinatorial properties of Convex Hull and how algorithmically we find Convex Hull and why is this good for Convex Hull and so on. Any questions before that? Very good. Okay, we are having a set of we talked about Voronoi diagram, namely we have a set of points. We want to subdivide the plane into regions such that for every point, site in this case, we define the region of all the points for which every point Q inside the region of P2 is closer to P2 comparing to the distance from Q to any other point. That is, P2 is the closest hospital, if these are hospitals, among all the as long as point in the cell of P2 are the ones to consider. That is, so in the cell of P4, if you'll ask a point that live in the cell of P4, who is your nearest hospital, the answer would be P4. That was a Voronoi diagram. It has lots of interesting application. We talked about data structures for point location. Data structure will help us quite a lot. For example, we have a map of states. I want to, in logarithmic time, land somewhere in the map and be able to answer in which city did I land, in which face of the map have I landed. And of course, I want an answer in quickly. Log n will be nice. Linear time will be way too long. We talked about point in a polygon. How can I find if a point is inside a polygon? We used the trick that essentially said, I want to ask whether Q is inside the polygon or not. I'll shoot a ray. I'll find where the ray intersect each one of the edges of the polygon, measure whether the number of intersections along this line is odd or even, because if I reverse the direction coming from minus infinity way outside the polygon and I hit one edge right here, meaning I enter the polygon. I hit another point, I exit the polygon, I enter the polygon once again, and I can enter, but the parity tells me, have I exit the polygon or not on my way from infinity to Q. Let's talk a bit about convexity. I think that everybody has a pretty intuitive idea what is convexity, but there are still ways to do it wrong. Formally, a shape S is convex if and only if pick any 2 points P and Q inside the shape, look at the segments connecting P and Q, this whole segment should be inside the very same shape. That will make the shape S convex. That is a property of with every 2 points, the segment between them is inside the shape. This property must hold for any pair of points P and Q. This shape over here, this polygon over here is not convex because there are segments that are fully inside the shape, but there is also a segment from here to here that needs to exit on its way from P to Q. Right? If I move P right here and Q right here, then I will, my segment is not fully inside the shape, so it's not convex. And as I mentioned, the opposite of convex is not convex, as opposed to the belief that the opposite of convex is concave. It's not the case. There is no exactly such thing as a concave shape. There are concave functions, however, but not concave shape. Disk is convex, circle is not. Right? Circle means that if I'll take any 2 points on the circle itself, circle is the skin of the disk, the boundary of the disk. Put 2 points on the boundary of the disk, on the circle, and the segment between them is completely outside the disk. It is completely outside the circle. It's inside the disk, but outside the circle, so a disk is convex, but a circle is not. We'll talk a bit about application of shortest path, application to robotics, of course, where we are given 2 points S and T, and we want to find the shortest. And we also give the location of furnitures in the room, or mountain in a terrain, or buildings, or whatever. And I want to find the shortest path in 2 dimensions or 3 dimensions that start at S and reaches T and avoids hitting any of the obstacles. I mean, I have a very, very tiny point Roomba, and this Roomba needs to Roomba robot, and the obstacles are furnitures of the room, and I don't want to hit any one of these obstacles. It will start as a completely toy problem, but it will go very quickly into basic problems of motion planning for pretty complicated robotics, robots with, in plural, set of robots with multiple degrees of freedom, or one robot that has several degrees of freedom of lots of joints and supposed not to hit obstacles or not to hit other robots. Okay. Range searching, more on data structures. Problem given a set of points in the plane. Think about them, prepare a data structure, meditate on this point. You have some time to prepare it. Make a special data structure. Try not to use too much memory, such that when I'll give you a query point, I need an answer quickly. When I give you a query region, say a rectangle, say a disk, I want to know quickly how many input points are there inside my query region. And I need an answer quickly. Right? I don't want to go over each and every point of P and ask, is it inside or is it outside? Especially if I just need the count of how many points living here. I'll give you the same query but located somewhere else. Again, I want the answer to my query quite fast. Much faster than the naive bound of check each and every point. Is it inside? Is it outside? So the output will be the subset Q of the set of point P, which are containing inside the query region R. Oh, sometimes I want the sum or the number of points, not the points themselves. Sometimes I want to ask either a point at all, or is it empty, emptiness queries. All these questions are relevant. Applications, for example, I'm considering opening a Walmart, a new branch right here in the center. I want to know who lives 5 miles away from me. If that's a location that if I'll start my Walmart, if I'll find my Walmart exactly in the center of the query region. Okay. Similarly, I teleported in my game. I landed at some point. I want to know who are the players other agents that are in my vicinity. We'll talk about visibility in a polygon. In this question, I have a polygon, and this polygon is not convex. You can see, maybe yes, maybe no, not in this example. This polygon might or might not be simple polygon. What is not simple polygon? This will be a non-simple polygon. It's not clear what is the input side and what is the output side of this polygon. But I want to have a clear definition of what is inside and outside. And I also want the polygon to be simply connected. Simple is different than simply connected. What is simply connected? Here is a polygon which is not simply connected. So my region inside this polygon are all the points but excluding the hole right here in the middle. Right? So the hole over there in the middle is not part of the polygon. So I start with a polygon, simply connected or not simply connected. Maybe this polygon represents the floor plane of a Gould-Simpson. These are what you see are walls of the Gould-Simpson. And I place a camera at P, and I said that this camera can see any point of the polygon, but it cannot see through walls. And the moment that I tell you where is the location of the camera, I define with it a region which the camera can see. And this region, in this case, will be here, this reddish part, if this is where the camera is at P. Namely, the camera can see this point over here. The camera can see this point over here. And if I'm just over here on this boundary, then my camera can still see me, but if I'm hiding in the orange region, the camera cannot see, because the camera cannot see through the walls of the building. Okay, and my question will be, place the minimum number of cameras so that the whole of Gould-Simpson will be monitored. Or place, or you have a budget of 17 cameras, what is the maximum area that you can cover in this way? Given that every point that you'll place a camera, it defines a visibility region that this camera sees. Okay, or another application to the same question is what I'm placing in P is actually not a camera, but it's a cell tower, or a 5G cell tower, or microwave, or anything that is disturbed by walls, and I want to place a minimum number of antennas, cell towers, in a polygon or in a terrain, such that you have line of sight to the antennas that you are talking to. Or any antenna has some coverage region that depends on the geography, on the topography near the antenna, and I want to again cover the region with cell towers. Lots of variants to this problem. By the way, the problem of finding the minimum set of cameras that see the whole building has a beautiful name, art gallery question. Art gallery question because the story behind it would be that you have a gallery, there are lots of expensive paintings and statues, and you want to place guards so that every point will be monitored by one of these guards. Many problems in computational geometry, we do not have an exact algorithm. That is, we can write an exact algorithm, we will not live long enough to see the algorithm terminates and come up with any meaningful answer. So instead, maybe you see only part of the screen. Oh, okay, so instead of exact solution, I will be willing to compromise for an approximate solution. For example, the TSP problem, traveling salesperson problem. In the traveling salesperson problem, we have a set of neighborhoods, set of locations, and you want to find some tour that will start at one of the points, go to another, go to another, go to another, and if you are going from A to B, you'll pay the distance between A and B, and you want to find at which order should you visit all these points so that the sum of distances will be as small as possible. The traveling salesperson needs to drive, walk as little as possible. And this problem, you probably know it already from graphs, but we can do, but the problem is well defined also in geometric setting, where the distances are just Euclidean distances. But the Euclidean distance between A and B is, I have to erase something, is x1 minus x2 square plus y1 minus y2 square, all this the square root, Pythagoras. That's the distance from the point x1, y1 to x2, y2. And that is what we refer to as the Euclidean distance. And now I want to find the tour that minimizes the sum of the Euclidean distance from A to B, from B to C, and so on. It's up to you to decide what's the order. So that's a problem that is NP hard and even in geometric setting, but you can do much more things in geometric setting than you can do in arbitrary graphs. Clustering, once again, you want to cover, for example, you have a set of points and you want to decide about a few clusters. Maybe each cluster is a disk. You want to find, you want to cover all the points with as few disks as possible, or with a pre-given set of points of a cluster, no more than 17 clusters, but you want these clusters to be as snug as possible. The disks should be as small as possible. And surprise, surprise, this problem is hard as well. Like, I think 99% of the interesting problems, but once again, approximations can give us a long way. Approximation here are different than heuristics. Just to state it here in anywhere else in computer science. When I'm talking about a approximation, I mean it's an algorithm that I can prove something about the quality of the solution that I'll get. Again, approximation usually comes with the accuracy ratio, with how far away from the optimum can I be. For example, in the case of the TSP, maybe it's hard to give an algorithm that will find the optimum TSP, but it's easy, very easy, to come up with an algorithm that will generate a path that is not more than twice the optimum length. Again, I will not find the tour with the optimum length, but it will be very easy to come up with a path that is no more than twice the optimum length. Maybe it's better, but not. I can prove that it's not worse than 2. That will be very easy. Anybody has any idea how to do it, by the way, in the case of TSP? Okay. We'll discuss it later in the course. For TSP, by the way, what you'll do is compute the minimum spanning tree, and for the minimum spanning tree, just work on the minimum spanning tree, do any tour that you can, and it will turn out that you are not doing more than twice the length of the TSP. Very simple proof. I'll cover it at some point. Finding nearest neighbor in the d-dimensional world. Every point is in 17 dimension because it's actually not a point by itself. It's a sequence of several points in 2 dimension. It's trajectory or GPS in 2 dimension, and I just concatenated these coordinations so it's point in higher dimension. Or it's the result of a few sensors that I measured at the same day. Or a point is a patient together with age, height, temperature, and so on, and a set of other measurements that I performed for this patient. And I want to find the nearest neighbor in this d-dimensional set of points. And it would be hard to find, if d is large, it will be hard to find the exact nearest neighbor, but we will see that approximate the nearest neighbor is still possible, which will allow us to go to dimensions that are in 2030 and are still very practical. If you try to solve it exactly or to use the Voronoi diagram directly without any trick, you'll get stuck after 2-3 dimensions. You'll run out of memory, but approximation can take you a long way. Okay, you can go on and on. There are problems in computational geometries all that are taken from many different domains and taken ways. And we are not lacking interesting things to do with these problems. But let's start with some basic concepts. To make sure that everybody is in the same page about how we measure running time of the algorithm, well, we are using the big O notation. I assume that you have seen it at least in 345, maybe in other courses as well. If you have never seen big O before, just talk to me after the class and I'll send you to a few references that will let you practice it more. Just to repeat or refresh the common definition, T of n is the running time of some algorithm for an input of size n. I want to sort n numbers. Here is an algorithm, say swap sort or insertion sort or bubble sort, and I want to say that the running time is order of, say, n squared. Or I want to say that the running time is order of n log n. And I want to say that the running time is order of 1, which means a constant. I want to say T of n, and that's very confusing. I'm saying T of n is order of something, but I'm writing equal to. And in European textbooks, sometimes you'll see that it's not equal. Instead, T of n belongs to some class of functions. But people are getting used to the fact that this is not really equal. It is a statement. T of n is order of g of n is just a macro, a shorthand of saying something much longer. What is this something much longer? I can find, when I'm saying T of n is order of n squared, I mean that I can find constant. One of them will be C1, one of them will be N0, such that for every N large enough, because I don't care about very small inputs. N is the size of the input. Every algorithm runs fast when N is small. I'm asking what happened about for big data when N is becoming larger and larger. Then to make T of N is order of N squared, to make it a true statement, I need to show you these two constants, C1 and N0, and to prove to you that for every N that is larger than N0, T of N is no larger than this other constant that I showed you, C1, times G of N, what I wrote over here. For example, N squared. What's the meaning? That here is the graph, the green one is a graph of N squared. Sorry, the green one is a graph of N squared, yes. The red one is the running time of this algorithm. It's the worst running time, the worst input, as long as the input is of size N, and N will become larger and larger. For each one, I'll find what is the worst, the slowest input. And to make this definition true, after N0, the running time of the algorithm is no more than this constant times N squared. Okay, the running time is bounded from above by N squared times some constant. What is this constant? You know, it's the unit by which you are measuring the time. It's different unit if it's months, if you're measuring it by months or by weeks or by microsecond and so on and so on. It accumulates for this one, it accumulates for, are you programming in C or in Java? Are you programming, are you good programmers or bad programmers? No matter. I want to know what is a, we'll use the term asymptotic running time. I want to see what this graph of the running time looks like when N is becoming larger and larger, because if I have one algorithm that runs in N squared and another one that runs in N cube, then there will be a point at which the N squared will be faster than the N cube algorithm, no matter what the constants are. Again, one algorithm that runs in N squared, another that runs in N cube, no matter what the constants that we play with are, there is always large enough input for which the N squared is faster than the N cube. Let's talk about orientation, a term that we are going to use again and again and again in the course. Those of you that took linear algebra will recognize that this is a determinant. We don't need this observation at the moment. Here is the question that I'm going to ask. I have 3 points, x1, y1, x2, y2, x3, y3. People from your direction, the fonts are all good when you're looking at it? As I meant.
Yeah, I mean, I can see.
Okay. Okay, cool. So I take these 6 numbers, the 3 coordinates, and I'll put them in this funny formula, half x1 times distance between the y's and plus x2, distance between these y's, and so on. You're getting some number. And what can I say about this number? Well, this number, the absolute value of this number is the area of this triangle. The absolute value of this number is the area of the triangle that these 3 points generated. And what we will find very relevant is that if I look at the sign of this expression. These numbers can be positive or negative or smaller than 0. Well, the sign tells me what is the orientation if I'm going from x1, y1 to x2, y2 to x3, y3. Am I walking counterclockwise, or am I walking clockwise? Sorry, or am I walking counterclockwise? From 1 to 2 to 3, 1 to 2 to 3. Here I'm moving I'm moving counterclockwise, CCW. Here I'm moving clockwise from 1 to 2 to 3. Okay, so that will be a nice property that I can use at the sign of this expression, and it will tell me at which orientation the 3 points are with each other, clockwise or counterclockwise. What can I conclude if this expression happened to be 0? What can I say about the points?
It means that there are two vectors on each other.
They are collinear. If this expression is 0, the only way is that the triangle has 0 area, which happens only if the 3 points are collinear. So area equals 0, meaning the 3 points are collinear. Area equals 0, meaning the 3 points are collinear. Okay, I'm hearing voices for myself in the back. And here is another question. How I have a line here is a segment that goes from x1, y1 to x2, y2, and think about the line that go through this segment. And here is a point P. How can I know if P is on the right side of this line or the left side of this line? Where the sides are respect of, if I'm walking from x1, y1 to x2, y2, will I see P on my right hand or will I see P on my left hand? Oh, this is completely collinear. Well, I'm not, so I will check what happened if I let P have the coordinates x3, y3, and I'm checking had I turned right in the middle point. When I walk from x2 to x2, y2, from x1, y1 to x2, y2 to x3, y3, what happens right here? Did I turn right or did I turn left? Is my car is turning right? Do I need to turn the steering right? Or do I need to turn the steering right, left, had P being the other way around? Which is exactly means is a triangle that these 3 points define. At which orientation is this triangle go? If this is P, then the orientation is clockwise, meaning that the expression that I'll get will be that it's smaller than 0. It should be negative. Okay. Yeah. Now, there is another way to solve this question. Let me show you another way to solve this question. I'll just clean the board a bit. We had P1, we had P2. There is a line that goes through P1 and P2. This is x1, y1, x2, y2. And there will be another point. I didn't draw it yet. The point P, P3. And I want to ask, is the point P above the line or below the line? And there are other ways to answer this question. Instead of using this hairy long term, I can ask, let's find the equation of the line. The equation of the line L. Does anybody know if I am streaming to YouTube? Will I also have the same delay that I have with Twitch? Twitch now introduced 30 seconds, so you can either participate interactively or participate but hear me 30 seconds later. You know any other streaming service that doesn't introduce this delay? There must be gamers here. Nobody knows. I'll check. Anyhow, if you want to check it on Twitch, at least the quality might be better than on Zoom. If you want to keep both open, I am alone algorithm on Twitch. Alone ALG on Twitch. Okay, what will be the other way of solving the line? I'll first want to find the equation of L, and the equation usually will be written as y equals, and now comes the slope of the line, which is y1 minus y2 divided by x1 minus x2. This is a constant. It tells me what is the slope of the line, which is the ratio between this edge and this edge, how high versus how what the slope. And this is what we know when we define line as A plus some number B that I should compute that tells me how much I move the line up or down. But my troubles start already with this equation. However, once I have the line as y equals ax plus b, then who are the points below the line? The points below the line are all the x and y, such that y is large or equal than ax plus b. Every point that is on or above the line will satisfy its y value is larger than a times x plus b. Why? Because if I'm exactly on the line, then this equals this, and if I'm adding some positive y, then I'm moving upward. Right? So I can express this line in this equation. Sometimes it's unavoidable, and solve this equation and find if my point is above the line or not. It's doable, but let's see what is the issue. And the issue is a horrible operation of division. We hate division. Why do we hate division? Because especially in geometric setting, division do operations that we don't expect. Division can cause you to look at the following expression. Take some x, any number x, and multiply it by 1 over x. What do you expect this expression to be? You know from math. X times 1 over x equal 1. Is this what you'll get on your computer? Maybe yes, maybe no, depending on if x is very small, then in your first computing 1 over x, it's a huge number, and you only have 64 digits, 120. 126 if we are using double float. only these many bits to represent it, then even if floating point arithmetic, you're losing some digits of what is actually 1 over x, and now you multiply it by x again, and which is, as we said, very small, and you are getting something that is close to 1 but not exactly. But in other terms, other algorithms, this little numerical error is rarely a terrible issue. I'll show you an example where a slight numerical error, actually I'll show you today, slight numerical error are bad enough to to break down the algorithm completely. It will cause some cascading effect that will force your algorithm completely, and what you thought that you sent to the 3D printer as a sphere turns out to be just what turned out to be half a sphere which is hollow from the inside, for example, and you didn't want it. Errors of this type. So we try to avoid division as a rule. If I'm looking at this system over here, I need to compute delta y divided by delta x. Now, this might be large, this might be small, and I'm running into this problem of numerical stability. So how can I avoid it? It's not always possible to avoid it, but if I just want to compute the orientation, then this expression at least just use multiplication, subtraction, addition, but no division. So it's much, much more stable. And people are willing to sacrifice a lot for the numerical stability. Namely, there are languages and libraries and people that makes a lot of money out of it from taking algorithms that runs very fast, makes them run much slower, but guarantees that there are no numerical errors on these solutions. Okay, yeah, we already talked about it. To know if the point is on the right side or the left side, we are just asking what is the orientation of going from P1 to P2 to the third point P3. Are we turning right, going counterclockwise, going clockwise turning right, or turning left going counterclockwise? Convex Hull algorithm. Of course I forgot it. Yeah, I'll show you next time. This is not as slick as I planned it. Let's get back to the lecture. Yeah, demos. Good. So we know what is orientation, and we want a quick reminder what is convex and not convex, and I want to ask the following question. I have a set of points, to start with, points in the plane. S consists of the points P1 ... Pn, all points in the plane. They might be actually in any dimension, and I can define it in any dimension. At the moment, let's assume that they are all in the two-dimensional plane. And I want to ask you what is the convex hull of this point. And there are various ways to define what is the convex hull. The easiest one uses rubber band, at which I'm going to take the rubber band, put it around the points, put the rubber band around the points, make sure that all the points are inside the region that the rubber band is covered, and then let go of the rubber band, and it will just snag to these points, create this nice fence surrounding these points. Let's try it in a more formal way. The convex hull, abbreviated CH of the point of the set S, capital S, is a polygon which is the smallest convex shape C that contains S. That is, I need the convex hull to be convex as a set by itself. That is, every segment should contain the whole segment, every segment with endpoint in the convex hull is fully contained in the convex hull. And in addition, it is the smallest set. Smallest in what sense? It means that if I imagine another convex set, D, that contains S, D, this square, is convex. It also contains S, contains each and every point of S. Well, D also contains the convex hull of S. That is, the convex hull is in any convex set that contains S itself. It's the smallest in this way. Okay, so this is the convex hull of the point, the smallest convex set that contains S. And I can give you another definition of what is a convex set. An alternative definition would be the convex hull is a polygon with the smallest perimeter, smaller circumference, not diameter, perimeter, smaller length of the fence that contains S. And I didn't say anything about convexity here. Just said I need to wrap S from all around. I want the smallest length in the fence that surround S. You can prove it, but these two definitions are equivalent. It's the same set. Here is another definition. The convex hull of S is the intersection of all the infinitely many convex shapes that contains S. S is a set of points. I pick one convex shape that contains S. I take another convex shape that contains S, and I keep taking their intersection. I generate more and more and more such convex shapes, and I take the intersections. What is all the points that lies in each one of these convex shapes, and you are left again with the convex hull, the same polygons that we discussed all the time, where the rubber band snag. The analogy of the behavior of the rubber band is of course coming because the perimeter of the rubber band tries to be as small as possible. That's what rubber bands do. Here is yet another definition for which let's define first what is a half plane. You know what is a plane? A half plane is a region of the plane that I generate by first I'll specify one line somewhere. Every line will define a different half plane. And now I'll specify that the half plane of interest is a part below or to the left of this line. Or I can say it's a part above or to the right of this line, and then it will be the other half plane, the complement half plane. Right? So half plane is what you're getting when you're generating a line, and you take all the regions which on one side of this line. Okay, so formally, the most general way to specify each and every line is to write a line as ax plus by equals c. Ax plus by equals c is a way for me to generate every line in the plane. And if I write instead of equal small or equal c, then I'm generating all the points that are on one side of this line. Correct? And obviously, if now I have if I'm living in 3D, then I'm not talking about half planes, I'm talking about half spaces. That is, I'll specify a plane in 3D and everything that is on one side of this plane. That's a half space. And so on for higher dimension. Now, some lines you can write, most of the line you can write as y equal ax plus b, for example, y equal x plus 1, and if I'll instead of equal, I'll write larger or equal or smaller than equal, then again I'm specifying a half plane. The half plane for which the line y equals ax is defined. Okay, now when you know what is a half plane, I can ask for this half plane, are you containing the set of points S or do you not? Maybe you don't contain any point of S, maybe you contain some but you don't contain other. So let's look only at half planes that do contain each and every point of S, each one of the green points, and this was one arbitrary half plane. Let's take another half plane that also contains S, the red one. Let's take another one, also red. And let's intersect all these half planes. But you have to put in the collection each and every such half plane that contains S, and once again take their intersections. This will give you the convex hull once again. So the convex hull is exactly the intersection of all these half planes. Okay, makes sense, right? Any questions so far? Everybody understand what is a convex hull of a set of points? Convex hull always convex. Now, the reason that I called it a polygon was because the number of points, is finite. So the number of points is finite, then the convex hull will be a polygon that looks like a polygon. What's a convex hull of a circle?
A circle.
You are probably, most people will agree with you, but since I'm very obnoxious about this point, I'll disagree. The convex hull of a circle is not a circle, and remember the circle are all the points if we'll think about the set of all the points x, y, such that x squared plus y squared equals 1, this defines a circle. These are all the points whose distance from the origin is exactly 1. All the points whose distance from the origin is exactly 1. And circle is not convex.
Yes, hitting the circle.
So the convex hull of the circle is the disks of all the points that lives inside the circle. Exactly. So the convex hull of a circle is just the disk. But as I said, I'm a bit sensitive at this point. Most people will agree with you that there is no distinction. Okay. Some facts about convex hull. Here is my convex hull. The convex hull is unique because if there will be two such convex hull, you can take their intersections and it's also a convex hull and it's the same shape. The boundary of the convex hull of a point set is a polygon. We already said it. Who are the vertices of the convex hull? Each vertex is a point of S. However, you might have points of S that flies in the middle. Right? Not every point of S is also necessarily a vertex. You might have a point that lives inside the convex hull. Right? So the vertices of the convex hull is a subset of these points. And let's start with a naive algorithm for computing the convex hull. I gave you a set of points and I want to know what is a convex hull. And to compute the convex hull, I mean if this is a convex hull, what I mean is that I want to know who are the vertices of the convex hull of S and in counterclockwise order. That is, I need to know that P2 is a neighbor of P3, implying that there is an edge between them, and P4 I thought that I said in counterclockwise order, sorry, P1, P2, P3, P4, P5, I did it in clockwise, P1 I want to know it in counterclockwise order, meaning that I also know what are the edges of the convex hull, because if P3 the next point is P4, then there is an edge of the convex hull connecting P3 and P4. And there is lots and lots of applications about convex hull. We'll talk about many of them. And let's start up with an algorithm for computing the convex hull, and let's start with a very straightforward algorithm. I can check each and every line of the convex hull each and every line in the plane are all the points of S on one side of this line, and take the intersection. That is, apply the definition directly. But there is infinitely many planes and only few of them are really important. So let's try to define what are the planes that are actually important. So I'll say that if I look at the convex hull and look at these half planes, well, this half plane, this little hair that I added over here implies that this is a half plane that I'm referring to, and this half plane, this half plane contains a convex hull, but it will give you more information if I'll shift it until it will touch a vertex, but I still have infinitely many such half planes. On the other hand, what I really want to identify are half planes that not only that they contains all of S, but each one of them is passing through a pair of vertices, because there will not be too many of these half planes. I want to find these special half planes that are passing through an edge of the convex hull. Half planes that are passing whose boundary line passes through a pair of points of the convex hull. So let's do it in a brute force way, which will be, let's take every pair of points, Pi and Pj, from S. Every pair of points, Pi and Pj, or P and Q, they define a line that passes through this pair of points, especially if I assume that the one point can appear only once. I don't have 2 points that coincide. So there is one line that goes through P1 and P2. Then now I check, and we need to see how, I need to check if all the points of S are on one of the two half planes that this line defines. You have a line, there is one half plane on its right, one half plane on its left. It is true that all the points of S are on one side of this half plane? And if yes, then I'll orient the segment that defines the half plane so all the points are on its left, and after I'll find all and by doing so I just discovered an edge QP that is an edge of the convex hull. And now if I'll continue from P, I can find the next edge, and this way to build the convex hull by just gluing the edges of the convex hull one after the other. How many lines do I need to check? Well, it's a number of pair of points that you have. There are n square pairs of points. It's n choose 2 to be precise. N times n minus 1 divided by 2, such pairs. How can I find if all the points are on the same side of the line? Orientation, once again. I'm asking, going from Q to P to P1, there is some orientation of this triangle, either clockwise or counterclockwise. Going from Q to P to P1, there is orientation of this triangle. If all the points of S are indeed on the same side, then the orientation of all these points is the same. You're either always going clockwise or always going counterclockwise, but it takes linear time to do this check. But if you have one point on your left, and will be done in 3 seconds, if from P to Q to P1, I'm walking counterclockwise, but there is also a point P2 which is on the other side of the line. Then to go from P to Q to P2, what are you doing? You're turning to the left. So the order to Q will be, why am I doing this mistake? Once again, the order to P1 would be clockwise. The order from P to Q to P2 will be counterclockwise. So by placing the coordinates of all these points in the funny formula that we saw earlier, you're checking if all the points are on the same side. What's the running time of this algorithm? Well, it's order of n cubed, because there are n square pairs, and for each pair you need this linear check to see if this pair defines an interesting line or not. And moreover, you are in troubles if you have 3 points on the same side of a line, or on a line. If there are 3 points on a line, then it will require special treatment. So what could be a numerical error might cause you, the impact of numerical error might cause you to say that these 3 points, that this is an edge, this is an edge, and this is an edge all at the same time, and or even that 2 of them are and the other one are not, and it doesn't make any sense just because of orientation. Suddenly numerical error will say, and that's why numerical errors, the answer might be that this is not an edge at all. I ask you what is a convex hull, but if you follow the algorithm, it could be that this edge will not be reported at all, and what you thought that is the boundary of a whole solid is now becoming just the skin of it. So when we either give special treatment to the algorithm to handle this exotic unknowing cases of 3 points on a line, or we are making a much simpler solution that is general position assumption. And general position assumption will mean I take my input to start with and I shake it by tiny bit of amount, introduce a minusculous noise, just so things that are very likely to happen, redundant cases, will not happen in my input, at least when I'm studying the algorithm. I will say if I have 3 points on a line and I shake it just by tiny amount, minuscule, infinitely small amount, then one of the points will move away from the line that the other two defines. So these special cases, I don't need to worry about them. That is general position assumption. The same assumption will mean I don't have 3 lines that meets at a point. I will not have 3 points that are vertically one above each other in other algorithm, and so on. It will make our introduction of the algorithm much simpler to have this assumption, and then to add the treatment of the special cases is not too hard if we want to. Okay, so that's also introduction to what is general position assumption. Perfect. Questions, people? I'm running a bit late, sorry about it. Superb. Okay, for next meeting, I'll ask you to also take a look at the following of the slides to get a bit prepared, but I think that otherwise we are good. Thanks.